Okay. Ready? Hi, welcome to our 8 a.m. Media availability, Tracking Ice, the latest efforts to measure the polar ice sheets. Our speakers today will be Andrew Shepard, IMBIE's co-leader, professor of Earth observation at the University of Leeds, director of the NERC Center for Polar Observation and Modeling, and principal scientific advisor to ESA's CryoSat satellite mission. Eric Ivins, IMBIE's co-leader, senior research scientist at NASA's Jet Propulsion Laboratory, member of the science team for NASA's Gravity Recovery and Climate Experiment. And Torsten Marcus, project scientist for NASA's Ice, Cloud, and Land Elevation Satellite 2, chief of the Cryospheric Sciences Laboratory at NASA's Goddard Space Flight Center.
Is there a laser pointer?
There is.
Okay, great, thanks. Good morning, everybody. I have a sore throat, so you'll have to bear with me. I don't think I'll run out, but I've got some medicine here in case it runs out. So thanks very much for coming. We're really pleased to present the latest assessments of how the ice sheets, the polar ice sheets in Antarctica and Greenland are changing. It's an update on some work that we started maybe 3 or 4 years ago now as a community assessment, but people have been measuring the polar ice sheets for about 20 years with satellites, different sorts of satellites. In the early days, we relied on satellites that were not designed at all to look at the polar ice sheets. They were designed to look at the global oceans mainly. But today we do have dedicated missions and things are getting better. The certainty of our estimates has definitely improved. But of course, to give people a real perspective of how climate's changing, we need long-term records. So we still do depend upon the very old measurement as well. So I'll give this presentation just because that's convenient, and Torsten and Eric will take questions afterwards on different aspects of the research that we'll present. So I'm sure, because you're here at this presentation, you already know, but I'll say anyway, the polar ice sheets are an important barometer of changes in global climate. You just need to change Earth's temperature by a small amount and they melt. And they are also a contributor to climate change because, of course, any melting ice that rests on land can cause sea level rise. And we want to be able to tell people how much of that to expect and how much of that we might expect in the future. And satellite measurements are really important for both of those things because we can't survey the polar ice sheets. This is Anglo-centric, I apologise, that's where I live. But it gives you an indication of where of the scale of the problem. So we need satellites. We used to use airborne measurements, and we still do rely on airborne measurements, but satellites are the best tools to look at those. And it turns out that actually satellites are important measurements to constrain models of ice sheet behaviour, evolution, and these are the things that we rely on for predictions of future sea level rise. So we're not saying that in any case that the ice sheets will give up this much ice, but there's the potential to raise sea levels by large amounts, and it's really important to put bounds upon the potential sea level rise that we might see from the ice sheets. And that's really our job these days. It's not to tell people that you could expect 60 metres of sea level rise, because that's not realistic, but how likely is 1 metre of sea level rise? Those are the sort of questions we want to answer. At the time of the last IPCC report, there were acknowledged, and all of the last IPCC assessment reports, there are acknowledged deficiencies in our ability to predict sea level rise, and that's because the ice sheet models that we use to analyse the behaviour of the ice sheets and predict changes can't be coupled to global climate models. The spatial resolution is just too different. There's progress being made in that area. We were going to have an ice sheet modeler on the panel, but we haven't managed to get one here today because of various reasons. Progress is being made, and we hope there'll be improvements in the future. But right now, the predictions that we rely on for sea level rise over the next century don't really couple the best ice sheet models into them. And so the estimate of sea level rise due to instabilities in the ice sheet, which we can see in the satellite record, is really, really quite small. It's about 5 centimetres, the prediction in the last assessment report. And you'll read in the literature, in the media and news stories, that upwards of 1 metre could be possible. So the question is how do we marry those two things together? And the answer is there are processes that we know about that happen in the ice sheets. We can see them on land and from the sky and from space that can cause them to destabilise really quickly. So I'll just give you an example of a few of these. There's basal lubrication of ice flow. If you melt ice at the surface, it can actually drain to the bed of a glacier and cause it to slide more quickly into the ocean, and that's a positive feedback mechanism. Iceberg carving or ice shelf collapse, they're the same thing. If you carve a large chunk of ice from the front of a marine terminating glacier, you reduce the traction on the sidewalls of that glacier, and it can flow more quickly into the ocean. And an ocean melting, which can deliver quite a lot of heat to the ice sheets, much more than the atmosphere because of the specific heat capacity of water, very much higher than air, can melt the undersides of floating ice shelves, reduce the basal traction here, and all these things can lead to speed up of the ice, which can be a self-promoting activity. And so we know these things happen, but the models used to make predictions of future sea level rise that are coupled to the climate changes don't incorporate them. And so there needs to be progress. We use satellites, various classes of satellites to measure the ice sheets. We use satellite altimeters, which measure the changing shape of the ice sheet, and that's a really good indication of how they're fluctuating. But that's not mass, that's just volume, and we have to convert volume to mass, and that's the greatest uncertainty. We have to make some assumptions there, and that leads to the biggest error bar in our measurements. We can use a technique called the mass budget, and that allows us to difference the amount of ice that's pouring into the oceans through glaciers from the amount of snow that's arriving or runoff that occurs. And that's been vastly improved thanks to the availability of satellites that can measure the speed of ice from space. And again, that relies upon a regional climate model estimate of the amount of snowfall, and that's the largest uncertainty in that technique. And then we have gravimetry, GRACE satellites, which can measure the weight of the polar ice sheets, and that can tell us the total amount of mass change as a function of time. They don't have very fine spatial resolution, but they have good fidelity in the measurement of mass change itself. The greatest shortcoming of that technique is that it integrates the fluctuations in snow and ice mass. We need a model to separate those two things out if we're interested in separating them, and we are, because snow is weather and ice is climate. And also GRACE weighs the Earth beneath it as well, and the Earth changes as well because of mass transports in the mantle and rebound of the lithosphere since earlier times. This is how the ice sheets look today. You might have seen this sort of plot before. It's a colour scale map of the rate of elevation change. This is just from one of the techniques, it's CryoSat. It gives a really good picture of where the ice sheets are changing. But as I mentioned, it has its shortcomings because we have to convert the elevation and volume changes to mass. But we know that there's rapid thinning of ice here in West Antarctica. We know that there's some thinning of ice in the Antarctic Peninsula, the warmest part of the continent. We know that, generally speaking, there's thinning around most of the periphery of Greenland, thanks to surface melting, but also there's some dynamic instabilities in certain glaciers, Jakobshavn Isbrae, Helheim Glacier, and Kangerlussuaq Glacier. And a study published just last month informed us that a glacier here in the northeastern sector of Greenland has started to speed up as well. So there's dynamic instability everywhere in the ice sheets today, and that wasn't the case 20 years ago. So these parts of the planet do look different to how they used to look. So lots of people make the measurements of satellite measurements of the ice sheets from space, and we set up this exercise called the ice sheet mass balance comparison exercise. Mass balance is the amount of ice mass stored in the ice sheets, and mass balance is a term that we glaciologists use to explain whether or not an ice sheet is gaining mass or gaining ice or losing ice, and the corollary of that is sea level will be lowering or rising as a consequence. We call it IMBIE for short. It was the first community assessment of sea level rise. It was supported by European Space Agency and NASA as a contribution to the last IPCC assessment report. We take all of the data that's been collected and make good use of it, and we replace what was then about 40 or 50 different estimates of ice sheet losses with just a single record that people can trust because it's a community assessment. Before we did that, before we performed it, we wanted to compare whether the different satellite techniques agreed, and this chart here just shows the various ice sheet regions: Greenland, the Antarctic Peninsula, East Antarctica, West Antarctica, Antarctica as a whole on both ice sheets. And these bars are the estimates of mass loss from different techniques and their error bounds. And in all of the areas, the techniques do agree when we match the spatial and temporal domains with one another. So that's really helpful because it tells us that we can rely on integrating them. They all have some strengths to them. They're not just weaknesses. And that allows us to add all these things together and produce this curve of sea level rise from the polar ice sheets. We see that over the 20-year time period, the total contribution to sea level has increased as a function of time. Antarctica is responsible for about a third of all sea level rise. Greenland, from the polar ice sheets, is about 2/3, and in total, about 11 millimetres we estimated in 2012 had arrived from the ice sheets together. We also noted that in the early 1990s, the ice sheets weren't losing a lot of ice, about a third of a millimetre per year of global sea level equivalent. That's about 10% of the sea level trend. And in the late 2010s, 2010, that had tripled. So the total sea level contribution is on the up, and they're now responsible for about a third of all sea level rise. So what can we do? And that data set's freely available. What do people do with these measurements? Well, this is a nice study that was published a month or two ago, which is a numerical model of Antarctica that can capture the variability in these glacier systems. And it was constrained with our measurements to improve the certainty of the sea level predictions as a function of time. So what this shows is a map of the retreat of the ice sheet under various scenarios. There's a 5% chance that the ice sheet will retreat to this orange level, 33% to the green level, and a 95% chance that it will retreat to the white level. You don't need to be able to see that because it's quite small. The numbers are, there's a 5% chance that Antarctica could give up 30 centimetres to sea level in the next century. That's really a much higher sea level contribution than the IPCC assessment, but of course it's a small chance. The question is do you want to act on that chance or not? There's a 50% chance that Antarctica will give up 10 centimetres to sea level over the next century. So the measurements that we can provide numerical modelers and climate modelers really go a long way to helping them improve the certainty of sea level projections. In the first exercise, we had 10 satellite missions, about 54 years of overlapping measurements, but 20 years in total. And now we have much more. We can go backwards in time because we can make good use of earlier satellite missions. We can go forwards in time because time has elapsed since the last exercise. And we know that there are new missions on the horizon which will give us even better measurements. So we can do much better. We can probably do 40-year record of climate changes in the polar ice sheets, which is a really good climatic record. And that's when modelers start to make good use of the data. In the past, we had about, well, before we performed our exercise, we had about 40 estimates of ice loss from Antarctica. This is a plot of different, Greenland, of different estimates of ice loss from Greenland. So in the 1990s, these two studies put Greenland in a state of balance. And in the late 2005-2010 period, most of these studies estimated that Greenland was losing about 200 gigatons of ice per year. That's a sea level equivalent of about 0.5 millimetres per year. Since then, we thought that people would stop making estimates of mass balance, but they got really excited about it, and there have been twice as many estimates since then. That's good. It means that the field is active and we can make good use of those measurements. What we can do, and this is not a formal assessment, this is something that similar to what the IPCC did, we can just take those measurements and calculate the weighted mean, balancing the different techniques against one each other. This is the way we did this before. And this is an interim assessment of the sea level contribution from Greenland. You can see that the rate of ice losses increased over time but has abated over the past few years. You might have seen that in some studies that in 2012 Greenland hit a hiatus period and didn't lose a great deal of ice. Similar thing for Antarctica. Before we performed the exercise, there was a bunch of studies that showed the same sort of thing, the ice sheet in a state of approximate balance in the 1990s and then starting to lose up to 200 cubic kilometres of ice per year since then. And we've had a whole bunch of other studies as well. And most of those have adjusted the ice loss down, so more positive. We can average those and we get a curve, time-varying curve, in the same way to Greenland of the mass loss. And then we can integrate those and add them together to produce the same curve of sea level rise from the ice sheets over the past 25-year time period. What we see is that the rate of loss has increased in both ice sheets, and it's up by about 20% in the past 5 years, which is consistent with the pace at which the ice losses were accelerating over the 20-year period we had before. So now Antarctica has contributed about 4.3 millimetres to sea level rise in 25 years, and Greenland 10.1. And that's the time period that we had in our first assessment exercise. So we've extended it in time, but we've also improved the certainty of the measurements within that shaded area as well. So it's all great. In the future, the space agencies have invested in dedicated missions to properly survey the ice sheets. So the European Space Agency is launching a new altimeter next year, Sentinel-3, that has an improved spatial resolution which can look at the edges of the ice sheets where most of the ice losses are occurring, and they're complicated terrain areas. NASA and the German Space Agency are launching a follow-on to GRACE in 2017, and that should give us continuity in those important GRACE measurements of mass loss. NASA are launching a follow-on to ISAT, ISAT-2 in 2017. That will be fantastic. In case you don't know, the ISAT mission a fantastically capable laser first flown around Mars, but the mission failed to meet its original intended requirements, and the laser burnt out, so it had to be running campaign mode. The data that were collected was still really fantastic for glaciology, and it gave us a real insight into how a fully functioning system could really improve things, and I think it's going to be great to see that satellite launched. It really was the first dedicated mission to look at the polar ice sheets, ISAT, from any space agency. And NASA and the Indian Space Agency are launching a new SAR mission in around 2020 that will give us continuity and measurements of ice velocity. In the intervening time period, NASA have been flying airborne campaigns over Greenland and Antarctica. These are really important because they tell us other things about the ice sheet as well. They tell us about how thick the ice is. They tell us how much snow is falling on the ice sheets, but they can also be used to provide an interim measurement of the volume change, bridging the gap between the ISAT-1 mission and ISAT-2. And there are now really detailed surveys of Greenland in particular, and the rapidly thinning parts of Antarctica, to give an airborne measurement of the mass changes as well. And I'm certain that these will factor in our next assessment. So the achievements of the project, the techniques do agree with one another. So if somebody tells you that the techniques don't agree, that they're wrong. They do agree. If you match the spatial and temporal domains of the measurements, they equal each other within 1 sigma uncertainty, which is pretty remarkable in science. Combining the missions provides a single community assessment, so people don't have to pick from 150 different studies. And that's a difficult thing to do if you don't know the details. And of course, we want people who are not satellite specialists to use the data, and they won't know the details. The accuracy of our assessment is 10 times better than the spread of the individual studies themselves, and so that's really important. People can know that the certainty of the measurement is as good as it can be. We know that there are challenging areas in East Antarctica and West Antarctica, and those are the things that we concentrate most of our efforts on these days to improving our estimates of mass imbalance in those places. As I said, the combined ice losses tripled between 1992 and 2012, and we think that there's been a 20% increase since then. So we're launching this new activity today at AGU. It's going to be an open community exercise now. Anybody can participate. We expect it to be annually updated so that it provides a fundamental climate data record for the wider scientific community, but also stakeholders. There are lots of agencies who want the latest assessment of ice losses from the polar regions because they might be making decisions about coastal protection. And this activity is now going to become more streamlined and coordinated by a dedicated committee. So the data that we've calculated so far has been released and used by lots and lots of different studies. It's a high impact paper, but also it's freely available online, and it will continue to be so. So I hope I didn't overrun too much. Take any questions, but please direct them at my colleagues on the panel as well, because they're just as involved in this as I am.
Great, thank you. We'll now open up to any reporters in the room who have questions. Please raise your hand, and when you ask a question, please state your name and affiliation. Are there any questions in the room? Okay. Are there any questions on the chat? No?
Do you want to ask a question?
Okay. No. Any other questions? No? Oh, one over there.
For Andy or Eric.
Oh, can you please use this?
Tom Wagner from NASA. For Andy or Eric, I didn't realize that there was a hiatus in Greenland mass change. Could you just tell us a little bit more about that?
So in 2012, if you look at the Grace record, I mean, you may know more about this than I do. Do you want to talk about it?
Yeah, there was a period in 2012 when it would appear as though annually we'd been seeing mass loss change each of the previous 10 years of Grace measurements, and we didn't see it that year. It's gone back since that time to ice loss kind of as usual. So we wouldn't make too much of that, but it is an interesting feature that we did see in the data. And it seems to be corroborated with a change in climate overall, surface mass balance that characterized the entire region.
It makes it... Yes, that's correct. It was in the winter of 2012. There was more snow arrived, and so in the following summer that wasn't outstripped by the amount of melting. But it just serves to emphasize the importance of long data records, because if the ice sheet stops to lose ice and those data are available to the public in real time, people draw conclusions that climate change has ended really quickly, for example, and have done. And so to have to be able to place those measurements in the context of a 20-year, 25, maybe 30-year time series is really important.
Okay, are there any other questions from the room? Any questions on the chat? No. Okay, thank you. That concludes our media availability. The next press conference will be at 9 o'clock on fracturing future Himalayan seismic hazards, insights from earthquakes in Nepal. Thank you.